Hi kiddos, this is a video on implicit differentiation, which is used for differentiating when you cannot or you don't want to explicitly solve for y. So before we start, I want to remind you of two things. Okay, so if I gave you that and I asked you to please go find the derivative of y with respect to x, we've been using this notation for a little while now, so I hope you're comfortable, dy dx, you would happily come along here and say that that's a 2x and the derivative of sine is cosine, and you'd circle smiley face and move on. But what if I had given you this instead? Now, I know and you know this is the same thing, and I could add the x squared back over to the other side, but I want to show you what you've been doing that maybe you didn't know you've been doing. What we're going to do is we're going to go do an operation on both sides of this equation, and that operation is differentiation. We're going to differentiate both sides of this equation with respect to x. And it's not so bad. I mean, I know it might look scary, but the derivative of y with respect to x is dy dx. That's where it comes from. Then I have a minus here. This is still 2x equals, this is still cosine. So derivatives are operations. So all you're doing is applying it to both sides. We could have done that back up here. We could have put in a ddx and a ddx as in my operation. So all I did is rearrange, and I could rearrange it back as I needed to. All right, that's one thing I wanted to remind you, is that differentiation is an operation. We're doing it to both sides of an equation. The other thing I want to remind you before we get into implicit is about chain rule. What if I asked you to differentiate some function squared? Well, you just came out of a bunch of chain rule practice for the past 3 days, so I hope this isn't super scary anymore. But you've got an inside function, which is f of x, and an outside function, which is that it's being squared. So outside in, we would pull the power, leave this alone, and then raise it to the first, which I won't write. Inside function is f of x, so we're going to multiply that by f prime. All right, that's just a chain rule reminder and differentiation as an operation reminder. And now we're going to put both of those ideas together in something lovingly called implicit differentiation. So here we go. I've only got 2 examples here because there's plenty more that I can pull, but it's just the same thing over and over. So here is an equation. This is a conic. I don't know if you remember about conics, circles, ellipses, parabolas, hyperbolas. This is actually just the equation of a circle, and I guess theoretically you could solve it for y, but it would be really messy, and I don't want to, so I'm not gonna. We're just going to go take the derivative. Your instructions would be to find the derivative of y with respect to x. So I can't get y alone and then just differentiate both sides. So I'm just going to dive in and differentiate now. It's an operation. I can do it as long as I do it to both sides. And it starts off not super scary. Derivative of x squared with respect to x is 2x. Derivative of 4x with respect to x is 4. Okay, now I'm scared. You need to think of y. If it helps you, you can think of y as just an f of x. So this is a function being squared. If we took the time to complete the square on x and y and then rearrange and solve for y, for the conic, we would get y equals something with x's in it. It is a function of x. I mean, we all took Algebra 1 once where we remember y's and f of x's are kind of interchangeable. That's still true here. All right, so when I do my derivative on y squared, it's going to be a little bit more involved. I've got to pull the power on the y, pull the power, subtract 1, times the derivative of the inside. The derivative of the inside is y. The derivative of y is the derivative of y, dy dx, minus this guy. Maybe you're not scared of him, but it's 3 dy dx's, negative 3 dy dx's, for the same reason. All right, equals 0. Derivative of a constant, 0. that is the calculus. That is the new calculus for today for this lesson. I do want to take you through the algebra of solving. Like we're supposed to go find dy dx. We need to solve for dy dx and get it alone. So I'm going to take you through that algebra once, and probably not from the other question I have for you. But I'm going to start by subtracting everything that does not have a dy dx on it. So I'm going to subtract that from both sides. Those are gone. Now I have 2y dy dx minus 3 dy dx, algebra, algebra, algebra. And then I'm going to factor out the dy dx from the left-hand side, and then divide this over, and I'm done. So dy dx equals negative 2x minus 4. So this is new. Like this, the way this answer looks is new, because I don't think I've ever worked a question up until just this second where I had y's in my derivative answer. And that happens. This just means that your rate of change is not just dependent on x, it's also dependent on y. So it depends on where you are on the graph, x and y value. All right, that is implicit differentiation. I'm going to throw one more example up here. It's not new, but it does kind of cover all of our stuff again. So here's another one. Plus xy minus 4y equals 11. I don't even know what that would be if I graphed it. Probably really ugly, so I'm not going to. Let's go take the derivative of both sides with respect to x. Okie dokie. I got this to start. This is not so bad. It's very normal. 3 secant x tangent x plus, this is a product rule. I got two things being multiplied. That's a product rule. So product rule says, first I write it, derivative of the second. Derivative of y is the derivative of y. First derivative of the second plus second is just y. Derivative of the first, dx dx is 1, so I won't write times 1. And then finally, minus 4 derivatives of y equals 0. Okay, I won't take you through solving this for dy dx, like getting dy dx alone. You could. It's not terribly different than the one above, but I just won't waste time. I do want to point out that I could have solved this one for y before I started. I would have gotten this if I move everything over and factor out the y from the other terms. And I can differentiate that too. I have to do a quotient rule. So I don't know that one's necessarily better than another. It's whatever you prefer, but there will be cases where you cannot solve for y and you have to do it implicitly. And then there's probably more cases where you don't want to solve for y because you just make it worse and the derivative gets too complicated. All right, enjoy. See you soon.